In section 6.4, we are looking at graphs and of logarithmic functions. So we looked at graphs of exponential functions. Now we're looking at the graphs of the inverse. We noted that for a logarithmic function, y equals, this seems to be a mistake, y equals log of b to the x power is the inverse of the exponential function y equals b to the x. Thus, we have the following, right? We know that the domain, here's another typo, of log base b of x is the range of y b to the x, right? And because of those inverses, right, they switch off. And log base b of x is the domain of y equals b to the x. So in other words, right, when we're looking at, if we think of the characteristics from the previous sections when we were graphing the exponential functions, in this particular case, for log base b of x, we have a domain, it's supposed to be an m, there we go, domain of 0 to infinity and a range of negative infinity to infinity. All right, so so given a logarithmic function, identify the domain. We're going to set up an inequality showing the argument greater than 0. So we want to make sure that it's going to be greater than 0. We want to solve for x and write the domain in the interval notation. So let's take a look. When it says the argument, what is it talking about? Well, in this particular example, it's talking about what is being plugged in. So the input, what is being plugged into the function? And so in this case, it's that x plus 3. So we're going to set the argument to be greater than or equal to 0. So x plus 3 must be greater than 0. And the reason for this is if you consider this, right, if x plus 3 did equal 0, that means that 2 to some exponent must equal 0. But if you know, you can plug in any value for this exponent. If you plug in 0, if you plug in negative values, negative 100, right, or a positive values like 2 or 5, there is no value you can plug in here that will give you the answer of 0. Because the only way we can get 0 is by multiplying by 0 itself. So that means that this domain, or our input, must be greater than 0. It cannot equal 0. Okay, it has to be greater than. We're looking for positive values here. So what does this mean? That means we're going to subtract 3 from both sides, and this tells us that therefore x must be greater than negative 3. So if we look at this in terms of a number line, right? If this is 0, here's our negative 3, it will be an open circle, and we are looking at all values this way. So because of that, this tells me that the domain is going to go open, parenthesis, negative 3 all the way to infinity, and this is our domain. Okay? All right, a little bit more complicated, but let's try to do the next one. Now, because this one's a little bit trickier, I first want to make sure that everybody catches we're taking the argument 9x minus x squared, and we're setting that to be greater than 0. Here we do have a quadratic function, so let's go ahead and get that x squared in the front. Okay, so we can see that we do in fact have a quadratic function. So we're going to have to go ahead and factor this out. So what does this look like when we factor? Well, they have a leading a factor in common, which is our x. But let's go ahead and pull out a negative x. So when I pull that out, I get negative x, and then I'm left with x minus 9 is greater than 0. So when we factor this, right? Actually, let's come over here to the side real quick. So let's say we're going to factor quadratic. So when we set up to factor it, let me change colors here. This is blue. We are going to have negative x minus 9. So what are the values of x? This is going to be equal to 0. So this tells me that negative x must equal 0, and that x minus 9 must equal 0. And so therefore x in this one must equal 0. So when we're thinking about the quadratic function, it's thinking about graphing it, this is telling me that at 0, I have an x-intercept, and at 9, I have an x-intercept. And because I have a negative here and a negative here, this is telling me that my quadratic is in fact upside down. So it's going to look something like this. Okay, so really what this is telling us is because these are our x values, that means I have 3 potential choices for my domain. Remember, I want the entire domain to be greater than 0, right? But this is kind of broken up because I can't have it equal 0. So that means that that's exactly what these values equal. So I can have something over here on this side. I can have something over here on this side, or I can have the middle. So my question to everybody is, if this is A and this is region B and this is region C, where is the function going to be greater than 0? Answer that question. All right, hopefully you can see that the function is going to be greater than 0 in this area B, right? So if I looked at domain in terms of intervals here, this interval here would have gone on from -infinity to 0. This interval here would go from 9 to infinity. But in both of these intervals, A and C, my function is negative because it's coming downwards, right? So the only place where this function here is going to be greater than 0 is between 0 and 9. This is the only place it's going to be positive. So therefore, my domain is going to be 0, 9. Okay. And again, it goes because we set that inside to be greater than 0, and then we factored it, found the roots of that quadratic function, and then decided based off of the graph, right? And it's just a quick sketch from what we know about polynomial functions. Where is the function going to be positive, right? And we see that the function will only be positive between 0 and 9. All right, let's look at the next problem. It says graph, right? f of x is equal to log base 3 of x. So the best way to graph a logarithmic function is to your first step is going to be convert to exponential, to an exponential function. So this particular function, notice I'm going to take this, I'm going to set it, so if this was equal to y, for instance, set it, raise it to the y power, and it's going to equal x. So the exponential function would be 3 to the y power equals x. Now what we're going to do is we're going to plot some points. So here's my x value, and here's my y value. And notice, because we're looking at the inverse, we are going to plot backwards because we are going to treat the y as the input. Okay? So if I did something such as -1, if I plug that in here, that's going to give me an x of 1/3. If I plug in 0 here, that's going to give me an x value of 1. If I plug in, let's see, 1, that'll give me an x value of 3, right? Because I'm plugging them into the y value. If I do 2, you can see I'm going to get a x value of 9. If I do 3, you can see I'm going to get an x value of 27. Okay, so those are larger values. So let's go ahead and plot some of these. So at 1/3, we're going to be at -1. So at 1/3, we're going to be at -1. So something like that right there. Okay. At 1, we're going to be at 0. At 3, we're going to be at 1. So here's 1, 2, 3. We're going to be at 1. At 9, we're going to be at 2. And I could go off into 27, right? So if you remember, in terms of, let's go ahead and write plot points. And so our asymptotes here is where is my function limited, right? So can I plug in any value for x? Well, if I look back, remember my input has to be restricted by 0. So I want x to be, my domain basically is going to be x is greater than 0, or in other words, 0 to infinity. So I am going to have an asymptote. Let's do it a different color. I'm going to have an asymptote here at x equals 0. My function, though, is basically going to come and it's going to get really close to the asymptote. It's going to curve like this, and so kind of keep on going. So, okay. They say that if you take the palm of your right hand and you look at it, you can kind of see the logarithmic function kind of going upward towards your finger, towards the middle of your palm, towards your thumb. And then you can see the exponential function kind of coming across your pinky going towards your index finger on your right hand side. That's not true for everybody, but for a lot of people, they can see the exponential and the logarithmic function on their hands. All right, so our asymptotes here is going to be at x equals 0, and we can see that for the domain, we're going to go from 0 to infinity. For the range, we will be seeing negative infinity to infinity. Okay. All right, let's check out this graph on Desmos real quick. All right, so if I want to graph this, I'm going to go ahead and open up this, and we're going to go ahead and click on functions. And we're going to slide down to I don't want statistics. There it is. So we're going to do logarithm. There's our log function, and we were graphing log of 3. So, oh, log base 3 of x. So sorry about that. I clicked on the wrong function. Let's come back over here to functions. So we're going to come down all the way to calculus, and we're going to do log base a. So notice how that one has a base. We want to make sure we change that to 3. And here we're going to go ahead and input our x value, and then we're going to set that equal to a y value, and notice the function right there. So we can see that we do in fact have a horizontal asymptote here on the x equals 0, right? And if I zoomed in, we'd zoom in here really quickly, really closely is what I meant to say, not quickly, right? You can kind of see that that function, if we zoom in enough, we can see that our function is actually not touching that y-axis. Right, so it's not touching the blue there. Okay. All right, that concludes this section, graphing logarithms.